One of the challenges that we have when we have a network of climate observing stations, regardless of the type of station that it is estimating the volume of a storm over an area. Now this becomes very important when we're trying to determine how much rainfall actually fell, or snowfall actually fell, in a watershed where we have tremendous variability due to things like the orographic effect, or just due to the simple spatial variability that we observe so often here in the Truckee Meadows. And so essentially what we're given is point measurements. That means the measurements taken at single climate stations, and we're being asked to go from that to total storm volumes, which would still become measurements of length, represented as length, but they'd also be something that we would be comfortable representing as having occurred in the entire watershed rather than at a single point. Some other questions that we have then is that if we're going to do that, what factors dictate which methods would be best to apply given a data set that we might have? And then there's the issue of weighting factors. Weighting factors, which I'll define in a minute, actually are something that are very important in the three types of techniques that I want to talk about. And it's important to understand what they actually do when you apply them. And then in the three specific cases of the arithmetic average, the Tyson and isohedral methods, the question is, how are weighting factors determined to develop measurements or estimates of total storm volume from point estimates in an area? With storm volume estimation, one of the things that we're trying to accomplish is an estimate of the amount of rainfall that occurs over an entire area, given that we really only know something about how rainfall was distributed between several different points that might be part of our watershed, or part of our watershed network. And we're going to be considering rainfall accumulating on a watershed without worrying about how storms move or anything of that nature. We're looking at total storm volume. And this is what we see when we look at reports from individual rain gauges, whether they're the SNOTEL site or RAWS or Washoe ET. We're looking at rainfall accumulating on an entire watershed. And the question though is this, is that when we look at watersheds or areas like Hunter Creek, in which we have stations that have a tremendous amount of variability from the crest of the Sierras down to the Valley Floor and the Great Basin, how can we really use that information that we've gained, that we've paid for, to estimate the total volume of rain accumulated throughout a watershed? Which value do we use? Do we use the one at the top? Do we use the one at the bottom? Or do we use some combination of those? And this is really, storm volume estimation is all about techniques that we're using to combine bits of information that we receive at points to come up with a reasonable estimate of what's happening, for example, throughout a watershed that has tremendous variability on the boundaries. One way that we can do this is by simply doing an average or a mean. Ideally, the mean value is equal to, for example, the average of values from nodes of a conceptual grid. That means we might take a grid and put it over our watershed, and then take an average of all of them, which ideally, if you think about if you use the mean value theorem, one of the things that you see is that with large numbers of observations, the mean becomes closer and closer representative of the entire data set. Unfortunately, while we may have many sources of data, we hardly ever have enough that where we can rely on using mean values as being representative, especially in the Sierras where there's tremendous variability. So our measurements are irregular. They're not spaced in a way that would give us confidence that a mean value would be very good for estimating the total amount of rainfall in a watershed. And so we have to rely on methods to produce what are called weighted means. Weighted means are essentially developed like this. They have a weighting factor. Okay, that in this equation, it's represented as AI. In practice, all of the weighting factors, AI, lie between 0 and 1, and the sum of all the weighting factors is equal to 1. And this will be clear in just about a minute, I hope. The primary difference when we talk about weighted mean methods is in how we develop the weights to produce the average. Some common methods for developing averages include the arithmetic mean. Here there are equal weights assigned to the observations. The way we develop an arithmetic mean is by summing all of our observations and then dividing by the number of observations. And so our weighting factor then is 1 over the number of observations, in this case represented as 1 over n. So what that means then is that if we have 7 observations, our 1 over n is going to be equal to 1 over 7. We're going to do that 7 times. We're going to essentially multiply the sum by 1/7, which just means then is if we were going to multiply each value by 1/7, this is the distributive property again, if we were going to multiply each value by 1/7, if we sum up those weighting factors, 1/7 plus 1/7 plus 1/7, we do that 7 times, we're going to have a total sum of 1, which is one of the conditions for developing a weighting factor. But in this case, all the weighting factors are equal. In the Tyson polygon and isohedral methods, the weights are really assigned as proportions of the total area of the watershed that's thought to either be represented by a polygon that surrounds a rainfall station or within a zone, the area within a zone that's assumed to have an equal amount of precipitation. And I'll illustrate that in a minute. Here are the 3 techniques illustrated. And remember, there are many more than just these 3. In the top technique, our arithmetic mean technique, each value has this, each observation is given the same weight. In this case, there are 7 observations. We give each value a weight of 1/7. So what this means then is that we add 13 plus 12 plus 15 plus 13 plus 14 plus 17 plus 16, and then we divide the sum by 1/7, and that gives us our arithmetic mean. The isohedral method makes 2 different assumptions. First of all, we can use the information that we've been given. For here are 7 our 7 climate stations, and we can draw what's essentially like a contour to connect areas of the watershed that conceptually receive exactly the same amount of precipitation. Here we can see a line that connects the 13 millimeter observations in this watershed. We can see one that conceptually connects all of the areas that receive 15 millimeters and one that connects all the areas that receive 17 millimeters. Each one of those then bounds an area. In this case, the area between that's less than 13 millimeters is designated as A1. Between 13 and 15 millimeters is designated as A2. Between 15 and 17 millimeters is designated as A3. Each one of those areas, and then there should be one more area here, A4, that lies on the other side of the observation of 17 millimeters. We've essentially chopped the watershed into 4 different parts, one of which is fairly big, that would include A2, and one of which is very, very small, which would be A4, which is not illustrated here. And the big question then is how can we develop an area-weighted average that makes some sense in terms of presenting a single value to us that we can use for the entire watershed given this approach? Well, one is that we assume that, for example, in area A2, that the average of the 2 boundaries amount of precipitation fell. So what that means then is that the average of 13 and 15 fell in zone A2, which is 14 millimeters. That means that all across zone A2 we assume that that 14 millimeters fell for the entire zone A2. The same thing is true for A1, which would be between about 12 and 13 millimeters, and for A3, which is between 15 and 17, and for zone A4, not depicted here, that lies between 17 and possibly 18. The observation is not shown. The important part about that then is that the areas associated with each one of those rainfall amounts become the weighting factor for each observation, or for each assumed observation. So, in this case then, the total area included in A1 would be divided by the total area and multiplied times the amount of rainfall that we assume is distributed over A1, which would be 12 millimeters, or 12.5 millimeters. In zone A2 then, our weighting factor would be the amount of area included in A2 over the total area of the watershed times 14 millimeters, which would be the amount that we assume falls between the 13 and 15 millimeter isohets, and so on. And so what you can see then is that we've chopped our watersheds into different zones. The size of the zone determines the weighting factor that's applied to the amount of precipitation, and the precipitation amount itself is determined by the boundaries of the isohets that we've assumed connect areas of equal rainfall across our watershed. Same thing is true of the Tyson polygon method. The Tyson polygon method, though, preserves the original value of the observation at our station and simply surrounds that with a polygon that has a specific area. In this case then, our 12 millimeter station is surrounded by a polygon of area A1, and we do the same thing for all the rest of our observations, ending up then with about 7 polygons, and the total area of each one of those little polygons when added together should be equal to the total area of the watershed, which simply means then that the weighting factors, if added together, which would be the area of the subregion divided by the area of the total region, when added together will be equal to 1, because essentially we're adding up all of the subareas, dividing them by the total area, and that will be 1. This is an illustration of why we would use this isohetal, Tyson, or arithmetic averaging technique. The arithmetic averaging technique is of course very easy to use. But if we have tremendous variability, here we are looking at Alum Creek, which is the sister creek to Hunter Creek, and we're looking at a variation in rainfall observations between 2 inches and ½ an inch from the top of the watershed to the bottom of the watershed. And the important part about that is simply that which observation would be the best observation to use if we were trying to figure out for example, the proportion of rainfall that became runoff, or the proportion of snowfall that became runoff during a spring melt event. What we'd use is in this case I've illustrated the isohetal technique, which involves chopping the watershed into different pieces based on the presumed amount of rainfall that fell in each one of these little zones. We sum up the areas of the little zones, and we'll have a representation of the total area in this watershed. And if we use the area in the little zone divided by the total area and multiply that by the presumed amount of rainfall, which in this case would be the average of the amount of rainfall on both bounds of the isohets, we can develop an area weighted average that accounts for the fact that there's tremendous variability across this watershed. Accuracy of these techniques is both scale dependent and data dependent. If we have a sparse data set and we have a high degree of change across an area and our scales for representing the area are fairly coarse, then our accuracy will suffer. If we have an intensive data set, many points of observation, and we have very little variation in topography and other factors that actually influence the amount of precipitation that we receive, then accuracy may be much higher. When people have looked at these methods and 13 others that are much more complex, one of the things that they see is there's little difference in the results. It's important to understand, though, that the Tyson and isohetal techniques may not account well for really big orographic effects because of the assumption that the change in precipitation between stations is linear. Now, the important thing about that is that the arithmetic techniques may not represent those areas very well either. It really is highly dependent on the number of observations that we have that capture the variability associated with the orographic effect. So let's look at some of the questions that we had. How can we go from measurements at a point to estimates of the total storm volume in an area? We can do that with any of several weighting techniques that we use to develop average amounts of rainfall. The factors that dictate which methods could be best to apply include, first of all, the sparsity of the data network or the relative density of rain gauges, as well as the rates of change and the rates of change that we're observing in precipitation between one station and the next. Weighting factors accomplish one very important thing. They take data that we have that may be very extreme and give those data an extra weight in the calculation of the average, so that it draws the average more toward or away from factors that represent more of or less than or less of a particular watershed. And the weighting factors for the arithmetic Tyson and isohedral methods are determined like this. For arithmetic, the weighting factor is simply equal to 1 over the number of observations. For the Tyson and isohedral methods, weighting factors are determined by the amount of area inside of a watershed that's actually represented by each one of the subzones created by these techniques for chopping apart the watershed and assigning values for precipitation to each smaller portion.